All right, so we're going to explore GCF factoring and difference of squares in this lesson. These two concepts are both fairly short. I don't think this video is going to be super long, but they are not really related other than they are both factoring. So they're these kind of headings like under the umbrella of factoring. There's like factoring trinomials, GCF factoring, and difference of squares is like a special kind of factoring. So just like a heads up, if it feels like in the middle of the lesson, wait, what does this have to do with the other thing? They're both under the umbrella of factoring. That's what they have to do with each other, but they're not particularly related to each other. So we want to establish beforehand what are factors, okay? This is really important to know since we're going to be talking about factoring for a while anyway. Factors are the things that are multiplied in order to find a product. So we might think of if you've got like 2 times 4 equals 8, that 2 and 4 are the factors and 8 is the product. So when you're talking about factors, you're talking about these things that are being multiplied. Now, when the directions say to factor, so you're looking at your homework, you're looking at your test, and it says factor or factor completely would be a lot of times how it would be phrased. You are being asked to find them. So you're being asked to find the factors. Now, examples might be x squared. Okay, now I kept these examples to variables because I want to talk about numbers in a slightly different way. So we have, what do we have here? X squared. X squared is factored into x times x. So it has 2 factors and both of those factors are x. X squared y, that is all multiplication. The x squared will factor into x times x and then you would have the y. Don't overthink factoring when it comes to the variables. It's pretty much stretching them out. There we go. So what was multiplied to give me x squared? X times x. When it comes to numbers, okay, numbers we're going to think of just, it's not different, but it sort of is. We can factor the number 12 into several sets of pairs. And a lot of times when we're factoring, what we're looking for are those sets of pairs. If you are terrible at multiplication, and a few of you this year have told me straight up, you have never been made to memorize your times tables, this can get very difficult. I might put together just a multiplication table for you to use as a reference during class, but eventually this is something that you're going to need. You're not going to be giving like a times table on your final. So if I were to ask you, what are some factors of 12? Well, you might say 1 times 12. 1 times 12 is a factor pair. Some of you might say, well, I think 2 times 6, that's a factor pair. And the other one is 3 times 4. And we would say that those are all factor pairs. When we get to factoring trinomials, this is what we need to generate. We're going to generate the pairs, and then we have to pick the right pair. Now, the other way we could think of the factoring is something called the prime factorization, which means you're going to factor it so that it cannot be factored anymore. And to do that, you might do something like this and make a factor tree. So you might say 12 is equal to 2 times 6, and then 6 could be factored into 2 times 3, and then we'd bring that 2 down to the bottom line there. And so we would say the prime factorization is 2 times 2 times 3. And the cool thing about prime factorization is it doesn't matter how you get there. So we could say 4 times 3, and then this time the 4 would factor, and we'd bring the 3 down. And what you want to notice there is that it's actually the same collection of numbers. Now, it might turn up in a different order. So you might end up with 3 times 2 times 2, but of course that would be the same thing. So the neat thing about prime factorization is that it's always the same, even if you take a different path to get there. So we sometimes want that. And again, the other way we have to think of it is like the pairs of factors. Now, you might also see this. You might see 1, 2, 3, 4, 6, and 12 are I don't want to say the factors because that kind of implies that prime factorization, but you might hear are factors of 12. So you could list all of the factors of 12. The factors of 12 are 1, 2, 3, 4, 6, and 12. Notice that the 1 does appear as part of the factor pairs, but we don't include it as part of the prime factorization. And the reason for that is because we could do 1 times 1 times 1. We could do that. And it's also why I didn't pick the 12 times 1 as my base there, because that 1, like, it didn't break the number down at all. You're still sitting there with the 12. Okay, now these are kind of some subtle things. I'm tossing them out there. You've probably seen them before if you've made it to Algebra 2, but it's kind of a refresher on that. So what are we talking about with the GCF? Well, first off, we need to know what GCF stands for. GCF stands for the greatest common factor. Okay, so greatest, biggest, we're looking for the biggest of something. Common would be shared, and of course, we're looking for factors. Now, when we factor out the GCF, we are essentially undistributing. We've looked at some distribution this year, solving linear equations. Factoring is going in the opposite direction. So on the left there, I have a distribution problem. So we would have 3, and we would distribute the 3 through the parentheses, and we would get 3x plus 12. The factoring, you would be given the 3x plus 12, and you would have to identify what was multiplied through, and you would say, oh, it's 3, and you would go in that direction. So the factors there would be 3 and the x plus 4. So there are 2 factors. The 3 and the x plus 4 are the 2 things that are being multiplied together. All right, so how can we get good at doing this? All right, so here's a strategy for you. I'm going to outline the strategy, and then we're going to do a ton of examples so you can see how it works. So first of all, get the prime factorization of the terms. So everything you've got in there, you're going to prime factor it. Please make sure you keep track of where the pluses and the minuses are, okay? Because we don't want to get the factors all jumbled together. Circle all the common factors. Now notice I didn't say circle the greatest common factor. You're going to circle all the common factors to find the greatest common factor, because the greatest common factor will be the product of all the common factors. And then factor it out and see what's left inside the parentheses. So you're going to circle them all, and then anything that doesn't get circled is still left behind. Now, as you do these, you're going to begin to see the larger factors without doing the prime factorization. The prime factorization is a great way to visualize what's going on, but it's not where we want to live. It's not where we want to camp out. So as you do them, you are going to start to see those larger factors. This is good. This is where we want to go. Feel free to skip these steps as soon as you are comfortable and confident doing so. So I am going to be doing the prime factorization. We'll review it with the prime factorization, but the goal is for you to see, both of my fingers there, see both of the GCFs, okay? So we're going to take a look at this. So we have 5x and plus 20, and we want to factor out the GCF. Now to do that, we're going to prime factorization. The prime factors of 5x, that's pretty easy. That's 5 times x. For 20, I'm going to factor that into 4 times 5, and then the 4 factors into 2 times 2. So keep that plus sign there. And the prime factorization is 2 times 2 times 5. And then you look at both groups. So we have 5 times x and 2 times 2 times 5. Well, the common factor there is 5. And so that's what's going to come out. And then anything that's not circled is what's still inside. So I have the x, I have the plus sign, and I have a 2 times 2, which is 4. And so we have now factored 5x plus 20. It factors into 5 times x plus 4. Now, some of you might be saying, well, couldn't you have stopped right here and seen the GCF is 5, so you would be left with 4? Yes, absolutely. Yes, you can see that, and yes, you can do it that way. All right, next one. We have 6x times 9, and so 6 factors into 2 times 3, and then we have times the x. Make sure you're keeping that minus sign there. 9 factors into 3 times 3, and we look across at that, and we see that you see that I have a typo in my next one. Oh, I gotta make a note. Change it for at least when we do it in class. I'll have it right. Okay. Awesome. Anyway, we've got our common factor of 3. Okay. And so the 3 is what's going to come out. And then anything not circled is what's still inside. So I have 2x, I have the minus sign, and I have the 3. So 6x minus 9 factors into 3 times 2x minus 3. Now, this, I believe, was supposed to be a 10, okay? That's what I'm going to change it to, so it's a 10 now. Okay, now this one does require a little bit more prime factorization here. I've got the 12, so I'll just do this up here. 12 factors into 4 times 3, and the 4 is 2 times 2 times 3. So we're going to have 2 times 2 times 3 times the x, and make sure you keep that plus sign. And then 10 factors into 2 times 5. And we look across those and we say, what do they have in common? Well, I see that we have a 2 in common, and that's it, just the 2. So 2, and then anything not circled. So 2 times 3 is 6. We got the x, we have the plus sign, and we have the 5. Now, if you are able to look at that and say 12 and 10 are both even numbers, so I know they share a common factor of 2, and just factor that out and see what's left. Again, you're perfectly, clear to do that. On the next page or next column, we have 3x squared. So that's 3 times x minus 4 factors into 2 times 2, and then we have the x. So this time we don't actually have any numbers in common. We got 3 on one term and 2's on the other term, but we do have an x in common. And so my GCF would be x, and I am left with 3x. I'm left with the minus sign, and I'm left with the 4. All right. And I really am not seeing, I didn't write a problem that kind of did what I wanted it to do. Maybe that 10 was not supposed to be a 10. I'm going to backpedal on that, and I'm going to change it to something else. I think maybe it was supposed to be an 18. So you're getting this is a great video. Best one I've ever done. All right, so what do we have here for 8? 8 factors into 4 times 2, and then the 4 factors into 2 more. And so we're going to have 2 times 2 times 2 times x times y. The x squared breaks into x times x, plus 2 times x times y. Now, again, we're looking for everything we have in common. Well, I see a 2. I see an x. And I see a y. Ooh, this is going to be tricky. So 2xy, all of that comes out as my GCF. And then anything left inside is still or not circled, is still inside. So I have 2 times 2 is 4, and then I have x. Now, right now, we have a bit of a dilemma because I have that plus sign. The plus sign is still there. What is supposed to go over on that other side? So you see, everything is circled. So it's everything is circled. This should be a 0, right? Well, let's see. If I put in a 0, and then I try to redistribute, okay? So 2xy times 4x, well, 2 times 4 is 8. x times x is x squared, and the y, that looks good. But if I do 2xy times 0, that does not give me 2xy. And here's the little piece that we're missing. Remember I said sometimes we do the times 1? Think about it for a second. Can you do a times 1? Can you just put a times 1 there? Sure, you can put a times 1 there. Like, that doesn't change anything. And so what you're actually left with is 1. And now when you distribute the 2xy through, you'll get the 2xy. Okay, last one. We have 5 times x minus 5 times x. And we have a similar situation here. We're circling the 2 5s. We circle an x. So the greatest common factor is 5x. Anything not circled is still in the parentheses. But we have the x, we have the minus, and once again, we have that like situation where we need to remember, yeah, that's right, that was a times 1. All right, now I mentioned the one over here where I had the 10 and said you were committing to a 10, and then I'm like, no. I do want to show you one more thing before we leave this slide. I know we've been parked on this slide for a very long time. Promise we're almost done. Is I want to change that to an 18. I'll do an 18 in class. The reason for that is the 12 is 2 times 2 times 3, and then you have the x. The 18 is going to be 3 times 6, and then the 6 will be 3 times 2. So 3 times 3 times 2. And what I wanted to show you was when you have more than one number. So you've got the 2 in common, and you have the 3 in common. How does that factor out? Well, it's 2 times 3, and so we would factor that out as a 6. And then everything left inside is the 2, the x, the plus sign, and the 3. Okay, so I just wanted to show you one that had 2 numbers in there. Like, what would you do if you had to factor out 2 numbers? You would multiply them together. All right, so that's actually pretty comprehensive. Now, they can get messier than that. Like, people can throw in z's. I think on your homework, I throw in like one that's got 3 terms, but the concept stays the same. Okay, the concept is going to stay the same no matter what. And that brings us to our something totally different. So now to something different. So we have the difference of squares. So let's break down that vocabulary. Difference means to subtract, okay? So when you are finding the difference between things, you are subtracting, okay? And squares refers to something called perfect squares. Okay, so we have difference of squares. It refers to something called perfect squares. So we are subtracting some perfect squares. So what on earth are perfect squares? Well, perfect squares are something times itself, like an integer times itself. So for example, 1 squared is 1, so 1 is a perfect square. 2 squared is 4, so 4 is a perfect square. We could do 3 squared is 9, 4 squared is 16, and you could keep going like that. So we would have 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. And you might go beyond that. We don't see the ones that are beyond that like too often. But those would be the first 10 digits perfect square. But also something like x squared is considered a perfect square because it's x times x. And so those are perfect squares. So when we're talking about the difference of squares, what we're referring to is something like x squared minus 25. So we have that subtraction, and the things that we're subtracting would be somewhere in this list. Now remember, there's an infinite number of perfect squares. So just because I stopped at 10 squared is 100, I mean, there is an 11 squared, a 12 squared, a 13 squared. There's like a 25 squared. Now, as they get really big, you may or may not recognize them. So that's when you grab a calculator and you just have to kind of play around with it. All right, now the difference of squares results from multiplying conjugates. And we looked at this earlier. We said conjugates are very, very, very special. All All right, and I've got a couple pairs there of conjugates. So we have x minus 5 and x plus 5. And when we multiply x minus 5 and x plus 5, we get this x times x is x squared. Then we get negative 5x with the negative and positive 5x with a positive. And then we get the minus 25. So you can kind of see where the squares come from. They come from the x squared and the 25. There's your subtraction. And what happens is those two, when you go to add them, actually cancel out. So 5x minus 5x is 0, and you're left with x squared minus 25. And there's your difference of squares. And that actually happens all the time. So we'll quickly do this one. 2x plus 3 and 2x minus 3. Well, 2x times 2x is 4x squared. 3 times 2x is 6x. Then we have the same thing, but with a negative. Negative 3 times 2x is negative 6x. And negative 3 times 3 is negative 9. And notice those are going to cancel. And the things that I am subtracting now are perfect squares. 4 is 2 squared. X squared is x squared. And 9 is 3 squared. And so that's where we get these difference of squares from. So they always come from multiplying conjugates. Therefore, when we factor them into conjugates. And what you think about is what squared gave me this thing. So we'll go set up the conjugates. One's going to be a plus, one's going to be a minus. And we say, what squared gave me x squared? That's x. And then maybe like the trickier question, what squared gives me 4? Oh, that's right, that's 2. And so the factors are x plus 2 and x minus 2. Those are the two things that are multiplied. All right, we can do another one. We have one's a plus, one's a minus. It doesn't matter what order you put them in. So if you really want to put the minus first, like knock yourself out. So what squared gives me x squared? Oh, it's x. And then what squared gives me 64? That would be 8. And so that factors into the conjugates x plus 8, x minus 8. Now the next one's a little bit trickier, but math is consistent. So we're going to have a plus and a minus. And we say, what squared gives me 9? Oh, that would be 3. What squared gives me x squared? That would be x. And what squared gives me 36? That is 6. Okay, now you might notice that this is actually not factored all the way. And I'm going to leave that for your homework. I'm going to leave that. I'm going to leave that one for your homework to ponder that one. All right. Now, last slide here. So we're almost done. Try this one on your own first, and then we'll look at it together. Great. I hope you pause the video to try it on your own before just letting me do it. Now, this one is not the difference of squares because 2 is not a perfect square and 8 is not a perfect square. So if you remember our list of perfect squares, it was like 1, 4, 9, 16, and you'll notice that 2 and 8 are not on there. But what you might notice is that we actually have a GCF. If I factor this, it's factored into 2 times x, and then 8 will factor into 2 times 2 times 2, and we have a GCF. So I can take the GCF out, and I'm left with x squared minus 4. And now x squared minus 4 is the difference of squares. So we could break that up, and we have the plus and the minus. What squared gives me x squared? Well, that's x. What squared gives me 4? That's 2. And then don't forget that 2, that was at the beginning. And so for this one, you actually need to grab that GCF first. So you factor out the GCF, and then you can keep going. What you're left with is the perfect square. Now, the one that we just did on the previous slide, there was a GCF in there that we could have gotten first, and we probably should have gotten it first, except that I was trying to do difference of squares. Okay, so what about your homework? So for the practice set 1 through 5, just practice that GCF. Don't let number 4 throw you. You're going to factor them, except now you're going to have 3 things. So you're looking for something that is common to all 3. For 6 through 10, factor the difference of squares only. And I think I did try to keep that so we didn't have any GCFs in there. And then for 11 and 12, factor out the GCF and then keep going. And you'll notice 12 can be done 2 different ways. Can you find both ways? It's going to kind of harken back to the one that we just did. All right, so that's it. You guys know where to find me, and have fun with it.